sorted this chapter. First thing, concepts you would have seen already. So till now, this module will be considering resistors. So we know how to deal with resistors in parallel, resistors in series. So what if you could start connecting capacitors in series and parallel? So what happens? So in this circuit, as you can see, the capacitors here are connected in series to a DC source. Okay, and since the same current is going to flow through each capacitor because they are in series, they would need to have the same charge, because charge is nothing but the rate of change. You can derive a charge from the current, yeah, because charge is nothing but if current is just a flow of charge. So if the same current is flowing through all the different capacitors here, they would need to have the same charge. That's what this equation is showing here. Okay, and we know, of course, from Kirchhoff's voltage law that the EMF here is going to be the sum of the voltages. Now, one defining equation of a capacitor is Q is equal to CV, or if you just do subject of formula, get V is equal to QC. And if you apply these two results here, you can see now that the total capacitance you get, which is Q total over C total, yeah, that's what is your E. Yeah, if you replace E there, which is the total voltage in your circuit, it would be the total charge over the total capacitance stemming from here. And these are individual ratios. So anyway, V1 is going to be Q1 over C1, V2 Q2 over C2. So if you just replace here, you get this result there. And since we say this charge is the same everywhere, it means you can replace all the Q by, let's say, Q1, Q2, or if you want just by Q. So all of them are the same, and then they just cancel out and you get this result. So in a way, if your capacitors are connected in series, it is similar to the result you would get when you connect resistors in parallel. Yeah, if you have resistors in parallel, you're going to apply this formula that you invert, and then you add, and then if you want to get CT, then you again take the reciprocal. So this is what we get if your capacitors are in series. Now, this one is for capacitors in parallel. So if you apply similar logic here, if you have, again, if you got the current, if you have a main current going out here from your battery, and then it will split into I1, I2, I3. So anyway, I total now is going to be the sum of all this. Like we said, the charge is going to depend on the current, yeah, because the rate of flow of charge is current. Since the current now is being split into different paths here, the sum of these currents is going to give the total current. So in a similar way, total charge is going to be the sum of the charges now. So when you connect the capacitors in parallel, they would have the sum of the charges would be equal to total charge. It is different to what we had earlier for the series one. So if you apply a similar method we just look at, you're going to get this result now. So total capacitance, the sum of capacitance. So again, it's the opposite of what you would do for resistor. For resistor, when they are in parallel, you will apply the other equation, this one. Okay. Now, based on what you've just covered here, you can look at these different problems given. So if you're given capacitors in series, how do you work out the total capacitance and the charge on plate and the voltage across the capacitor? So the solutions are given in the lecture series, so I will send it to you. So very straightforward things. You should be able to do that, yeah, based on the equation we just covered. So this is the total capacitance, and the total charge, like we said, is going to be the same everywhere because the same current flows. Okay, so you can easily calculate this one, and once you get this one, you can calculate the voltage across each capacitor individually. Bearing in mind, of course, that the sum of all the voltages need to be equal to your battery voltage. Yep. This example here is for capacitors in parallel. So again, I'm leaving that to you, and all the workout, all the solution is given in your lecture series. So just briefly, so since the capacitors now are connected in parallel, the sum of capacitances will give a total capacitance anyway. And like we said, the formula is Q is equal to CV. Since the capacitors are all connected in parallel, they will have the same voltage across them as the battery EMF. That's why it's the same here. And then you just have to multiply the individual capacitances by the voltage across it. So you get the individual Q1, Q2, Q3. And since it is connected now in parallel, the sum of the individual charges will give us the total charge, and you can answer that. Okay. In this circuit, there you find a combination of capacitors in parallel and series. Yep. So again, if you assume a current going out, it goes through this capacitor C1 that's split into two paths. So you could easily combine these two capacitors C2 and C3. Since they are in parallel, you just sum them together and get 6 microfarad, and then you can now do reciprocal to get the total. C1 and the 6 microfarad, and from there you get a similar circuit as before. So again, the workouts are given there. So you can see the left capacitors here, and then from here you can do a very similar analysis to what you have done in the circuit where you have series capacitances, and you can work out that. Yeah. So I leave that to you to look at the workouts. If you have any issue, we can come back to it. Okay, so this is left as an exercise for you to work. Again, answers are given there. Now, one important point I want to stress here is in this question. Let's just read that together. Saying find the voltage across and charge on capacitor C1 after it has charged up to its final value. Now, when you connect a capacitor in any circuit, initially it is not charged, so it means it has no voltage across it. It will build up that voltage over time. So it's not like instantaneously when you connect a capacitor in the circuit, it's going to just immediately go to the final value. It takes time to charge. So we'll look at that later today. It's called transient of the charging. Transient means it's a stage in any circuit. It doesn't need to be a electrical circuit, even in mechanical circuits. You will study that when you do back to 4208 in your fourth year. So you have two stages in any circuit: mechanical, electrical, pneumatic, hydraulic, any type of circuit you take, or even in life, any process you find around it, you will always have a period of change before something stabilizes. So the stage where it is stabilized is called a steady state, and the stage where things are still changing to reach that state of equilibrium is called a transient. So transient is a stage where things are still changing. So as you connect a capacitor in a circuit, it is now starting to charge up to the final value, but stage where it is, the voltage is changing is called transient. Okay. So this question is saying find the voltage across and charge on capacitor C1 after it has charged up to its final value. That's a question. So in a way, when the capacitor is fully charged here, yeah. So in a way, current will stop flowing through it. That's an important observation. We repeat that. When a capacitor is fully charged, current will stop flowing through it because it has reached its final value. But as long as the capacitor is still charging, what will charge the capacitor? Is it current? So as long as the capacitor is still charging up, current will flow through it. That's important. But when the capacitor has reached its final value, current will no more be flowing into it because it has reached its final value. It is in steady state. So in a way, when a capacitor is fully charged, it means you can replace it by an open circuit because current no more flows. Yep, the voltage you find there, which is called VC here, is the final voltage the capacitor will take. It is not going to be 24 volts in this particular circuit because you have two resistors in parallel here, so they're connected in parallel. If you did not have this 8 ohm resistor here, then the final voltage you would get across your capacitor would be equal to 24 volts. We'll look at some examples of that later. But what I want to stress here is that was your initial circuit, and then at the start you can't replace the capacitor by an open circuit because the capacitor is still having current flowing through it because the voltage is still picking up. Okay, but when the capacitor is fully charged now, means it has reached its final value, it's not 24 volts in that case. That's what the question is asking you to find. But when it reaches the final value, the current will stop flowing. It means you can now see the capacitor has become an open circuit because current is no more flowing. So it's very easy now. If you want to find what final value VC would be, it's a voltage divider. You can find that the terminals here for the capacitor is actually in parallel with the 8 ohm resistor. So you will simply do a voltage divider and get the voltage across the 8 ohm resistor. So in that case, it's 16 volts. That means the capacitor will charge the final value of 16 volts. And when it's fully charged, you can represent the capacitor as an open circuit. Very important. We'll come back to this later, time and again. So I've just introduced it. I'll explain it again. Now, of course, once you've got the voltage to be 16 volts, you can just apply your equation Q is equal to CV. You get the total charge stored in microcoulomb. Yeah. So the units for charge is coulomb. Okay. Now, next thing. So what we've considered till now, all the circuits you've considered till now, just go back. All the circuits were for a capacitor which has reached steady state. Means it has already gone through the charging phase. It's not changing in the final value of this voltage. So it is fully charged. So all the things you have looked in now, all these capacitors there, you are assuming them to be fully charged. So for example, if I said here, the charge on capacitor C1, which is Q1, is 38.4 millicoulomb. So this charge corresponds to the charge that the capacitor would have when it's fully charged. So all examples we've looked at now are for steady state in the capacitor is fully charged. Now what we're going to look at next is the phase where it's actually charging up. Like I've said, this is called a transient stage. So we want to understand more now between the time the capacitor has 0 volts across it. Yeah. So initially, if you consider this circuit, for example, initially, so this switch, you have a switch in the circuit which can be turned to position 1 or position 2. Yeah. So initially, let's say it is not at position 1 or position 2, it is simply off completely. So initially, the capacitor is not having any charge. Now, at some time t0, you just put the switch at position 1. So when you do that at time t0, the capacitor has a voltage of 0. So initially, the capacitor has a voltage of 0. Then it starts picking up charge slowly, yeah, at some rate. We'll look at that in a few minutes in more detail. So the aim of this section of this particular chapter is to understand how the capacitor charges, so how it picks up voltage from being 0 to a final value of, in that case, it will be E, that capital E. Now we've just said why it charges to a value of capital E. We've just said the capacitor would initially have a current flowing through it when you close the switch because it is still charging up. But when the capacitor is fully charged, so it has reached its final voltage, then you can consider this capacitor to be open circuit because no current is flowing. So if you decide to open circuit this one here, no current is flowing, so no drop across the resistor, then by applying Kirchhoff's voltage law, you would infer that the voltage across the capacitor, which is open circuit at steady state, is nothing but E. If you apply Kirchhoff's voltage law across this loop here with a switch closed and a steady state, no current is flowing because the capacitor is fully charged, then you'll find simply you are measuring the battery voltage E. It means that in this case, VC is going to charge up to E. So what are we studying now? I will just go a bit into the theory is how can we model mathematically the transient of this capacitor charging being from 0 initially and then going to the final value. And we would also want to understand how IC changes. So current IC initially you would initially have an IC because this is what's charging up the capacitor, because IC is nothing but the flow of electrons which is collecting on the capacitor plate here. But as the capacitor starts charging up continuously to a final value E, the current will of course start reducing up to a point where it becomes 0. Okay, so we look at these two parameters as we go along. So there are some notes given there on what I've just explained to you of what happens when you close the switch. So you have electrons start flowing up here until a point where the capacitor actually reaches a value of capital E. So if this is at E and this is also at E in terms of potential, when there's no potential difference between the battery source and your capacitor, then if there's no potential difference between these two, the voltage, there will be no, you won't get any current because the current will flow when you have a difference in potential. Okay. Now this also means initially the capacitor here will be at 0 volts when you just turn on the switch, and this one is at E. So initially you expect to have a very large current flowing because you have the maximum difference in potential. This is at E initially, and this is at 0. The potential difference is going to be E itself. So it means the initial current to be maximum. But as your capacitor plate starts charging, so initially, if let's assume E is 10 volts, for example, and initially that's at 0. Okay, initially when just turn on the switch here. So initially the capacitor is not charged, it's at 0 volts. So the potential difference between your battery and the upper plate here will be 10 volts. So 10 minus 0, so it's a maximum difference. Maximum difference in potential means maximum current. Then the capacitor placed here starts charging, it becomes 1 volt, 2 volts, 3 volts. So as it starts increasing in potential, the potential difference between your battery and the capacitor plate starts falling. For example, if that's 10 here, it is 1, potential difference becomes 9. Then when this one becomes 2, it becomes 8, and so on. So as the potential difference starts reducing, your current will of course reduce in proportion because it's a potential difference which is creating the current. Now, ultimately, when the, let's say again, this is 10 volts, ultimately when this is 10 volts and this plate here is also 10 volts, the potential difference becomes 0 because 10 minus 10, then this is where your current stops flowing, the capacitor is charged. Okay, so just to recap, the initial current there, IC, will be maximum initially because you have maximum difference in potential between your battery and your upper plate of the capacitor. Okay. And your voltage initially is 0, the VC initially 0, and VC will start picking up until it reaches capital E, whereas the current will initially be maximum and it will fall to 0. So this is what you expect as waveforms. So your voltage across your capacitor would initially be 0, so it is not charged, and then it's going to pick up. Now, in a few minutes, we understand why it's exponential. Yeah, so we'll go into the mathematical modeling of this and give expressions to these different curves. But just to represent what we just discussed in terms of the voltage and the current, like we said, the current initially is going to be large because this is where you have maximum difference in potential between your battery and your capacitor plate. And then as your capacitor charges, the current will decay slowly until you reach 0, is where your capacitor is fully charged. So, and the VC now, the voltage across the capacitor would initially be 0 and then charge the final value. So just bear in mind, I hope it's clear based on what we just discussed in these two cases. So initially this is 0, it picks up to a final value of E. That's what we see on the curve, is 0 and picks up to a final value of E, the battery EMF. And the current initially is maximum because the potential difference is maximum. So maximum current initially, as you can see here, maximum current initially. Okay, and then it decays to a value. Now, what the maximum value of the current is E over R. So let's look what is E over R. So when you connect the switch initially, yeah, so this capacitor here can be short circuited initially. So what did we say initially? When a capacitor is fully charged, it's an open circuit, so no current flows. On the other hand, when the capacitor is initial, so when you start connecting when you close the switch there and this is starting to charge, initially you can replace this capacitor as a short circuit because this is where it is accepting maximum flow of current. Okay, so if you liken this one to a short circuit, it means what is left in the circuit is simply E and R. So if you apply Ohm's law, you get E over R as a maximum value of a current initially. Yep. So this is why the maximum value of a current is initially over R, and then it will decay, of course, as we said, as the capacitor charges up, the current will decay until we should see. Yep. So you can read the notes there. I will send the lecture series. What I've just described in terms of a rate of charging initially is highest because of a maximum difference in potential and so on. So you can read in your notes what I've just explained more or less. Okay. Now, this is what I've just explained after the capacitor is fully charged. So when your capacitor reaches a voltage of E, which is equal to the EMF of battery, then you have a situation now where no current will flow because there's no potential difference. So the charging current becomes 0. And it means at this point onwards, you can replace your capacitor by an open circuit because it's an open circuit that has no current flowing through it. Yeah. Yep. So if I can just summarize how you can represent a capacitor at the start of charging and at the end of charging. At the start of charging, you can represent it as a short circuit. This is where you get maximum flow of the maximum current. And then finally, when it's fully charged, you can represent it as an open circuit. So this is where you don't have any current flowing. This is why it becomes an open circuit. And if you apply this, just like I said, if you apply Kirchhoff's voltage law in this loop here, since no current flows in the circuit, the voltage drop across your resistor with 0 volts is equal to IR. So the whole battery voltage would need to be across the capacitor. Right? Kirchhoff's voltage law, you get the same. Okay. So this summarizes very well what you just said. So initially, you can represent your capacitor as a short circuit. This is where you get maximum flow of current, which is E over R. Yeah, because if you apply again Kirchhoff's voltage law or very simple circuit here, you have E and you have only R there. You replace your capacitor by a short circuit, and then so it is E over R, the maximum current. And finally, when the capacitor is fully charged, you replace your capacitor by an open circuit, so no current flows, so your circuit is in steady state. Okay? So it's the start of a transient, it's the end of a transient. When you reach in this state there, it means you have gone to steady state now. There's no transient. Now, what happens between these two states? So between the current being 0 and then final, so this is called transient because the current is changing, and this is again called a transient because the voltage is changing. So as long as you have a change in the parameter which you are analyzing, in this case as a voltage of your across your capacitor or current flowing in the circuit. So you can see in this stage there between this time t is equal to 0 when the switch is turned to position 1 until this stage there, this is called a transient. So something is still changing. Same comment here. So for the voltage, so initially here the voltage is 0 and then it keeps increasing. So this is the transient part, and then at this point onwards, you find your voltage is not changing anymore because the capacitor is fully charged. Then this is the steady state. Okay. So I hope it's clear now what the steady state is and what is transient. Okay. Now, what are we doing next is we're trying to give mathematical equations for these different waveforms we've seen for the current and for the voltage. So I'm just going to switch now to Excel to just do a small exercise with you to explain these curves you're seeing there. Then this will become very simple. Yep. So I'm just shifting now to Excel. So I'm going to just want to decide with you. I hope you can see Excel sheet. So we're just going to plot these two graphs there. Y is going to 5 exponential minus x, and then y is going to 5 into 1 minus e power minus x, and see what happens. Now, before we do that, if you have studied exponential functions, especially negative there, because we've seen the current decays. So when you have a negative exponential for x, we know this means exponential decay. So from what we have studied in mathematics, if you analyze this one, of course, your x will be positive because, for the example we're considering here, the x will actually be time. Yep. So in a few minutes, we're going to look at the curves in the PowerPoint slides. So your x there would actually be time, and we know time has to be positive. At some point, you turn on the switch. So this is where time starts and t goes to starts at 0 and then increases. So this is why we won't consider any negative value for x in this case, although x could go to negative values if you consider this expression as in a mathematical sense. But since you are talking here of time, we won't go in the negative domain. Okay. Now, before we start sketching these two graphs there, we know from mathematics that the first one is an exponential decay. So if you replace x by 0, we get e power 0, which is 1, and then 5 times 1, so the initial value is 1. And then as you start increasing x, you expect this the value of y to keep reducing. So the initial value here with 5. The final value now when x goes to infinity, so exponential minus infinity is a very small value, almost 0. So you expect this function to start at 5 and then to decay to 0. On the other hand, now in the parentheses here, you have 1 minus e power minus x. So again, if you replace your x by 0, so you get e power 0, which is 1. 1 minus 1 is 0. So initially, it means this expression here would start at 0. And then as your x goes to infinity, so as time goes to a very large value, you expect this exponential of minus x to go to 0, like we've said here. But 1 minus 0 means it will be 1. When you take 1 times 5 means it's going to tend to a final value of 5. So it means this one is a decaying function. This one is an increasing exponential graph. Yep. So let me just try to sketch this. We take x. I'm going to start x at 0, like we said, and then let's just put a small increment. So if we just add this is 0.05, and then we just increment that to, let's say, value of let's say 10, a bit more. Maybe it's too much now, so let's stop at 10. Okay. And then I'm going to write expressions now for these two functions. Let's do both of them. So this one we said is equal to 5 multiplied by, so you have a function exp in Excel, exponential of minus x. So x is this column there. So you get your value here, and just double click. So we get all the values. So I'm going to write for this one as well. So this one is equal to 5 multiplied by, in parentheses, 1 minus exponential of minus x minus, again, the first column. We have two brackets to close now, and we get this value. I expected it's 0 initially, and then it's going to expect to increase. So I'm just going to plot these two graphs now on the same axis. This is what we get. And as I've just explained to you, so this one is a decaying one. So the first one, so this is 5 exponential minus x. Like we said, it starts at an initial value which is high, and then it decays to a value which, as x goes to a very large value, in this case 10 is deemed to be large. In a few minutes, when we go back to the lecture slides, we understand what is large and what is small. We'll come back to something called time constant. So basically, as your x goes to large values, you see that the function is decaying to a value of almost 0. On the other hand, this one, like we said, it's an exponential graph. If you take 1 minus the e power minus x, so initially it is 0, and then it picks up until it reaches a final value of 5. So like we just discussed, the blue curve there would be the function, the mathematical function you would use for current, because we said current starts at maximum value and then goes almost to 0. Whereas this one is what you're going to use for the charging of voltage across the capacitor, because the value starts at 0 initially, but the capacitor is not charged. And then as your time goes larger and larger, it goes to a final value which corresponded to our battery EMF. Okay, So what I wanted to stress here was these two functions. Just you have to remember these two forms. These are the only two forms you will find in terms of capacitor charging. So you need to recall that if you just take a constant times exponential minus x, you're going to call it decay. Whereas if you take a constant times 1 minus e power minus x, this is going to be an exponential growth. So if you remember this, you will be fine. Okay. So let's shift back to our lecture slides. So you can see same graph there. Yep, same sort of functions, but in this case we just have the exponential one, so we don't have a constant in front of it. This is why it is starting at 1. Same comment here, it's just 1 minus e power minus t over tau. In a few minutes we understand what is that minus t over tau. In our case, it was just x there and x. That's it. Now we are replacing it by minus t over tau. I'll explain that in a few minutes. Yep, and so we see that the final value will be 1 here because we are not multiplying by any constant. Now let's see what we are doing. On the time axis t there, we have something called tau. Now we're putting a parameter called tau. So now we have 1 tau, 2 tau, 3 tau, 4 tau, 5 tau, 6 tau, and so on. And we're replacing our x, which we have in our Excel sheet, by minus t over tau. So if you replace, for example, this one, so when the time is equal to tau, if you replace tau here and tau here, it means you get e power minus 1 and e power minus 1 there. So when you replace your t by 1 tau, you get e power minus 1. When you replace your t by 2 tau, means 2 times that constant, you get e power minus 2 tau, and so on. This is 3 tau, 4 tau. So in a way, we are replacing our x by minus t over tau. When you replace your t now by multiples of your tau, you are able to get e power minus 1, minus 2, and so on. Okay. So what do you find, for example, when you replace your t by 1 tau, you find that if you consider the exponential increase, so the final value which you are getting is 1 because there's no constant in front of it. We find that when you replace your t by 1 tau, you find that the value you get is 0.632, so it is 63.2% of the final value. If you replace your t by 2 tau and you just read this value off here, you find that it is almost 0.85, so almost 85% of the final value. If you replace it by 3 tau, you find that it is almost 0.94, for example, something close to 0.95. So this is 0.94, so 94% of final value, and so on. And one thing we can conclude from here is when you replace your t there by 5 tau, it is almost a final value. So it means we can assume that the function has reached the final value after 5 tau. You can assume that because if you have an exponential function, actually it never reaches the final value. If you think of it mathematically, an exponential function, if you replace t by a very far high value, yes, you can say that the exponential part becomes 0 or tends to 0. It's a question of a limit here, but mathematically it never goes to final value. So we're trying to infer here after how much time can we assume that the function has reached its final value more or less. And we find that 5 tau seems to be a proper value. 4 tau is close, yes, it is around 98%. But if you want to be more close, you would say 5 tau. 6 tau is too much, I would say, because 5 tau is enough. So from this, we can infer that after 5 tau, the tau, you can see it is it's a constant you are putting there. And when we take multiples of that and replace in the time, we are getting, let's say, e power minus 5, e power minus 6, and so on. So after 5 tau, we can assume your capacitor in that case is fully charged, or the current has fully stopped anyway. Yep. So this is what you can infer from this diagram. Just pay attention to this. So we'll assume that after 5 tau, your capacitor can be assumed to be fully charged, because you can see at 5 tau it is almost 1. And in the same way, after 5 tau, your capacitor current, the current flowing in the circuit, is almost 0. Important observation. Okay. Now, if you look at these two curves there and the curves we considered earlier, these ones, so they would have actually the same equation. Okay. So for example, here we find that the maximum value was E over R. So you won't have the expression e power minus t only now. It will be E over R multiplied by e power minus t over tau. This is what you have because the initial value is E over R. And here, for example, your voltage across your capacitor is tending to a value of capital E. So it means it's going to be capital E into, since an exponential graph, so capital E into 1 minus exponential minus t over tau. Yep. So what I'm just saying here is, if you look at these two graphs, for the maximum value of capacitor, it was E over R, the capacitor current. So it won't be 1 now. It's going to be e power minus t over tau multiplied by E over R. And this one, the final value, which the voltage across the capacitor is standing to was capital E, the battery EMF. So it's going to be capital E here multiplied by 1 minus e power minus t. That's all you need to understand. That's what I just said there. So it means the expression for your current there, we don't say decay function. So you will, since the maximum value initially is not 1, if it is 1, you would have just a 1 there. It's not 1, it is E over R. We've seen that. Now you can see now the next step we've done is we've replaced your tau by RC. So what is RC? Let's go back to your circuit, the very first circuit. So this one was your RC there. Yep. So when you connect the switch to position 1, the product of your resistance with the capacitor, RC, is actually the value of tau.